The next topic in kinematics of a particle in non-rotating coordinate systems is circular and spherical motion. And you can think of these as motions where an object stays a fixed distance from a point of like a center of motion. It's motion about a joint. Circular motion is when all the motion stays in a plane, and spherical motion is when it stays that fixed distance from the pivot point, but it's free to move in all three directions. In any case, in either of these two cases, the angular velocity vector can be defined as, well, we always call it omega. Whoops, not dot. Omega, and it's a vector. And the definition of this vector, angular velocity, is the time derivative of the angle about the point directed about its instantaneous axis of rotation and remember, being directed about the instantaneous axis of direction only limits it to two directions. It could be one way along that axis or the opposite way along that axis. And our direction is defined according to the right-hand rule. So, for example, if you have a circular motion this way, we know that the angular velocity vector needs to be perpendicular to this, so it needs to either be into the page or out of the page. And the right-hand rule says that it's coming out of the page. So this would be the angular velocity coming out of the page. And this idea is useful in describing motion about a pivot. We're going to see when we move into rigid bodies that really maybe the main reason this is so important to us is that it's also useful in describing the rotation of rigid bodies about a point, because on a rigid body, the distance that a chosen point moves about some other fixed point, some other chosen point, like its center of mass, can't move. That's the definition of rigid, really. Okay, so there's a couple things you need to notice about this definition of angular velocity. So notice. The first one is this angle has to be in radians. And does that mean you have to change your calculator to radians? Well, you might have to for other things in this class, but the radians mode on your calculator only determines how the trig functions are dealt with. So you don't necessarily have to do it just because you have something being measured in radians. It's only if you're taking cosines and sines of angles in radians. But we'll see some example problems where we do that too, and then your calculator does have to be in radians. The second thing you have to notice is that any circular or spherical motion has an instantaneous axis of rotation. that may seem sort of counterintuitive, but in fact, even if something is free to move in like a spherical path in all 3 dimensions, at a single instant, you can identify a plane that this thing, in which this thing is moving as part of a circle. And if you can identify that plane, then there's an axis perpendicular to that motion. And so you can identify that instantaneous axis of rotation. The thing that changes between 2D and 3D motion, circular and spherical motion, is in circular motion, the angular acceleration has to be in that plane as well. And so it has to have the same axis as the angular velocity. In spherical motion, on the other hand, the angular velocity and angular acceleration don't have to be parallel. So that's the difference. But no matter what kind of motion you have about a pivot point, you can always find an instantaneous axis of rotation. We're not going to talk about how to find it. In our problems, it'll just be given to you in some way or another, but you can always find it. And then the last thing that you need to notice is so I guess sort of related to number 2, in 2 dimensions, defining or imagining that function theta, that the way the angle changes with time, is easy. But in 3D, it's a little harder to picture. You still do have this plane that the motion is instantaneously taking place in. Sorry, that's not what I want to say. So in 2D, defining that that angle theta is easy to do. It's easy to picture what it means. And you can just calculate omega by taking the time derivative and then using the right-hand rule to make sure that it's in the right direction. Okay, let's do some examples. Okay, the first example, say that your function, your position function as a function of time, is equal to 10 times the cosine of 2t, 10 times the sine of 2t. This is circular motion in 2D, and we want to know what's our angular velocity. Well, this is a circular motion. The radius is 10, right? In order to figure out the angular velocity, we need to identify the angular position function, how the angle about that pivot point changes in time. And you know, probably can recognize that this circular motion, a circle is defined by radius times cosine of the angle, radius times sine of the angle. And so in this case, our angular position is just 2t. That's in radians. And so to find the angular velocity, we're going to take the derivative with respect to time of 2t, and that just gives us 2. The units there are radians per second. And now we have to figure out the direction. Well, this motion is counterclockwise. So the right-hand rule says that the angular velocity has to be this way. our coordinate system is like this, with z coming out. And so our angular velocity vector, since we know that omega is in the positive z direction, is going to be 0, 0, 2 radians per second. So now that we've defined angular velocity, we have to define angular acceleration. An angular acceleration is the same whether you're in 2D or 3D. So the angular acceleration, which is the Greek letter alpha, is equal to the derivative of the angular velocity vector with respect to time. And there's something you need to remember about the difference between 2D and 3D here. So notice, for circular motion, the angular velocity vector and the angular acceleration vector have to be parallel. If you have a full 3D motion, like a spherical motion, those aren't going to be parallel necessarily. So omega and alpha are either in the same direction or the opposite direction. If they're in the same direction, then the motion is speeding up. And if these are in the opposite direction, the object is slowing down. Okay, so let's do another example. Say that we have, let's see, so say that we have a circular motion defined by theta equals negative 5t squared. Then theta dot, which is going to be omega, is negative 10t. So that's in the z direction in a planar motion. So we can think of our angular velocity vector as equal to 0, 0, negative 10t. What about our acceleration vector? To calculate the acceleration vector, we just have to take the time derivative of the angular velocity vector, and that's 0, 0, negative 10. And again, we see this pattern that we're always going to see in circular motion. The angular velocity and the angular acceleration are parallel to each other. And in this case, we see that they're in the same direction. They're both in the negative z direction. So we know that this circular motion is speeding up. Okay, so what about, all the examples we've done so far have been circular motion. Now we'll do an example, a real simple one, with spherical motion. But if you have a motion that isn't, so the angular acceleration and angular velocity aren't parallel to each other, that means that this object is moving in a full 3D space. And in this case, most often you're just going to be given the velocity, the angular velocity vector. So let's say the angular velocity vector is 20t x, 5 in the y, and negative t cubed in the z. And we want to know what's the angular acceleration vector. Well, we're just going to take the time derivative of the angular velocity vector. And so we get 20, 0, negative 3t squared. Okay. So one of the most useful things about representing things in terms of angular velocity and angular acceleration is that it's a very straightforward process to figure out a particle's velocity vector or its acceleration vector from these angular quantities. So if you have a particle's motion expressed in terms of the angular velocity and the angular acceleration, and you know the particle's position, that's an instantaneous position relative to the pivot, then the particle's velocity vector at that instant is just omega crossed with that position vector, that r vector, and the particle's acceleration is equal to the angular acceleration crossed with that r vector plus omega crossed with the quantity omega cross r. This is the term, if you're talking about circular motion, this is the term that represents the tangential acceleration. And this is the term that represents the centripetal acceleration. And I mentioned this, but in order to use this, you have to know that that r vector is a vector pointing to the particle of interest from the pivot. And that pivot is the center of the circle or the sphere that the motion is happening about. Okay, so here's another example. So let's say that we have circular motion, and actually, let's say it's circular motion. And let's say that the angular velocity is defined by 0, 0, negative 2t squared. And say that we're given a radius of 5 meters. Okay, the angular velocity is in the negative z direction. That means that the motion is in the xy plane. And since it's the negative z direction, the right-hand rule says the motion is clockwise. And let's say that so this is just more information that's given in the problem. Let's say that when time is equal to 2.5 seconds, our r vector is equal to 0, 5, 0. So what that's saying is, say that the instant we're concerned with is right at the top of the circle. Okay, that's our point P. The question is, first, what's the velocity vector of that particle? Second, what's the acceleration vector? Okay, and that's all. To calculate the angular acceleration vector, we're just going to take the time derivative of this. And to evaluate the angular velocity, we're just going to plug 2.5 seconds into our function for the angular velocity. So we have 0, 0, negative 2 times 2.5 squared. And so you get 0, 0, negative 12.5 radians per second. And now we'll use the velocity formula for our point P. The velocity is equal to the angular velocity, 0, 0, negative 12.5, crossed with 0, 5, 0. And you get a value of positive 62.5. That's in meters per second, 0, 0. And now look at this motion. Does it make sense that the velocity vector would be in the positive x direction? Yeah, it's tangent to the circle in the direction of a clockwise motion, so that makes perfect sense. And now we want to calculate the acceleration of the point, so we're going to have to get the angular acceleration in order to use that acceleration formula. The angular acceleration is omega dot. So the time derivative of our omega function here, 0, 0, negative 2t squared, is 0, 0, negative 4t. And so if we evaluate the angular acceleration when time is 2.5 seconds, we get 0, 0, negative 10. And the units here are radians per second squared. And now we can plug these values into our acceleration formula. The acceleration of the point P is 0, 0, negative 10. That's alpha. Crossed with r, 0, 5, 0. Plus omega, 0, 0, negative 12.5. Crossed with the quantity, 0, 0, negative 12.5. Crossed with 0, 5, 0. And if you calculate all that, you get an acceleration vector equal to 50 meters per second squared, x, negative 78.125 meters per second squared, y, and 0, z. So what do we know about this motion? We know that at the instant we're concerned about, the angular acceleration vector is pointed in the same direction as the angular velocity vector. They're both in the negative z direction. So we know that this motion is speeding up. We know that this positive 50 meters per second squared is the tangential acceleration, and we know that this negative 78.125 is the centripetal acceleration. And it's also worth uh, recognizing that anytime you have an angular velocity vector that is purely a function of z, and actually, generally speaking, purely a function of any of these, it's a function of time, but it only has a non-zero function for one of these components. You know that when you take the derivative, it's only it can only be non-zero in that same for that same component. And that means that anytime you see an angular velocity that only has one non-zero component for a function, it has to be circular motion, because it has to be the case that the angular velocity and the angular acceleration are parallel to each other.